Good morning, good afternoon, good evening, good wherever you are, and welcome to the SNIA NSF Networking Storage Forum presentation. You've been framed, xPU, GPU, and computational storage programming frameworks. This is a live webcast, and welcome. So, who have we got talking with us today? We have quite a number of luminaries, and I'm going to go through them one at a time. On the left top, we have John Kim, who is the chair of the SNIA Networking Storage Forum, this very group that we're doing the presentation for. And he's the director of storage marketing at NVIDIA. Next to him, we have, and I'm just trying to find the, here we go. We've got James Reinders, who's an engineer at Intel, who's focused on parallel programming in a heterogeneous world. And specifically, responsible for the DPC++ project, which is a SYCL for LLVM, which is we will be covering a bit during this presentation. He's also got a book on it that's free for download, and there's a pointer in here that will take you to that book. We're also joined by Dr. Joseph White. Joe is a fellow with Dell's CTO office, focused on NVMe over fabrics, DPUs, which are data processing units, another one of these xPUs, networking and disaggregated infrastructure. He's worked for a number of companies. He's been around a long time and has a wealth of experience. He's also got a PhD in high energy particle physics, which is very unusual because I've actually got a PhD in how to get rid of magnets on the secondhand market from secondhand cyclotrons. You didn't know that, did you, Joe? Anyway, you got it now. We're also joined by Ben Walker, who's a technical lead in Intel's Storage Software Acceleration Group. He's been around in Intel for quite some time, over a decade, since 2011. He is a co-maintainer for the Storage Performance Development Kit, or the SPDK, and his areas of experience include NVMe over fabrics, RDMA, computational storage, wide variety of topics. We're also joined by David McIntyre, who's the Director of Product Planning and Business Enablement at Samsung, where he focuses, again, on computational storage and green computing solutions. That's the low power stuff. I'm Alex McDonald, and I'm your happy host for this hour-long session today. So who is SNIA? SNIA is an industry-leading organization of about 180 companies representing the storage networking industry. We've got about 2,500 active contributing members and about 50,000 IT end users and storage pros worldwide, of which you are a number. And welcome today. The NSF, the Networking Storage Forum, is part of SNIA, and we focus in specifically on things like Ethernet, fiber channel, InfiniBand, the actual physical pieces, the transport protocols over the top of it, like iSCSI and NVMe over fabrics. We cover virtualized, the software-defined storage protocols like block, file, and object. And we're all also interested, as everyone should be these days, in the security of data. This SNIA presentation has copyright associated with it. If you could read that in your own time, I'm not going to be going through it in detail, but basically it says to honor our copyright and that there are no warranties with this presentation. So without further ado, today's agenda, here we are. We're going to take a high-level overview of the acronym soup that is the area of frameworks. And we're going to talk in a little depth on some of these topics, but we're going to talk at a fairly high level and try and cover as much as we can about frameworks. We're going to be covering future topics. And at the end, I'll ask you to contribute to that conversation by asking you which topics in particular that you would like us to address in a future presentation. But for the moment, I'm going to pass over to John Kim from NVIDIA. John, take it away.
Thank you, Alex. So I'm going to cover specifically OpenCL and CUDA as development frameworks for accelerating access, mostly to GPUs. So briefly, what are these? So they're both frameworks for programming GPUs. The OpenCL also lets you program CPUs. And by a framework, I mean these are typically libraries with APIs. They may have compilers or compiler extensions for programming languages, and also different drivers for accessing the hardware. So I mentioned they can access programming languages. For example, If you use CUDA or OpenCL or ROCm, which is the AMD equivalent of CUDA here, then that lets you program in C or C++ or perhaps in Python or other languages. And use from these languages, you are then able to redirect some of the compute work to a GPU. And specifically, if you're using CUDA or ROCm, you can send it to an NVIDIA GPU or an AMD GPU. If you're using OpenCL, you can direct part of the compute work, the math intensive or graphics intensive portions, to either CPUs or GPUs. So that's one of the advantages of OpenCL, is that it works with hardware from multiple vendors. Whereas, as mentioned, CUDA only works with NVIDIA GPUs and ROCm only works with the AMD GPUs. So, of course, there are other different accelerators available, and you'll hear more about that. So you may have a DPU or IPU or FPGA, and there are other frameworks and other ways for getting to those, which you'll hear about shortly. So just briefly, there often is a question about what accelerator or what framework should I use? In this case, let's say I want to do the GPUs, and also what level would I program? Because typically these frameworks offer you access, or you have access to this hardware at different levels. You may have low-level access, for example, at a driver or low-level APIs. You may have mid-level access using libraries, or you may have a pre-created application, an application for AI or for graphics or for medical diagnoses or for vision, for computer vision or autonomous driving. These are high-level applications that are often available either from the GPU vendors or from third parties that let you access them at a high level where the application is already created and you can just use it or modify it. And then on the other hand, a library or middleware might be something like PyTorch or TensorFlow or Rapids or other types of libraries which give you fairly, advanced access to different types of machine learning or vision or AI or high performance computing. But it's higher than the driver level, but lower, but it's not a complete application. You still have to develop your application on top of that. So back to the question of which platform or which framework should you be using? I should really say framework here. I think that depends. You want a framework that supports the hardware you're using, or which could be just one vendor's hardware, or could be multiple vendor hardware from multiple vendors. And you need to know the type. So for example, if you want to do FPGAs, you would not use CUDA or OpenCL or ROCm. And then you may also want to see which types of libraries or applications are available if you are programming at that higher application or library level. And then back to the right side of the slide, the higher level access at the application level typically makes it very fast and easy, but you're limited to what's available and it gives you less flexibility. The lower level access, like at the drivers or APIs level, typically gives you more flexibility and potentially faster performance, but it takes a lot more work and more technical knowledge and expertise to program to accelerated hardware at that low level. All right, that ends my section. Let's turn it to James of Intel.
Thank you, John. So I'll talk a little bit about SYCL and oneAPI. Let me just jump in and give some definitions. So SYCL is a solution for heterogeneous programming in C++. It actually grew out of the OpenCL work. OpenCL had a two-level programming model that wasn't as composable and was more C-oriented. So when we look at solutions that are trying to give us a multi-vendor, multi-architecture approach, SYCL grew out of that with a strong affinity for C++. And it's standardized by the Kronos organization. It really does three things. It lets you, in your application, find what accelerator devices are available, manage memory sharing with them, and manage offloading computations. A couple of related topics, words you'll see thrown around, DPC++, which was mentioned earlier. It's an implementation of SYCL into Clang and the rest of the LLVM community. And yes, we have a book talking about that, using that compiler for more information. And but this doesn't give you everything you need to program, because this is very focused on capabilities in the C++ language, you also need libraries and tools and so forth. So there's an open, multi-vendor, multi-architecture approach to get things like profilers and libraries and debuggers, and that's called oneAPI. So together, these come together. SYCL is a way of doing things in C++. DPC++ happens to be one of the SYCL implementations, and oneAPI extends that to the things we need as developers to do this. It's exceedingly simple. Programs to do these computationally intensive things tend to look alike, regardless of what language you write them in. There really isn't a reason that Fortran or C or C++ necessarily has to give better performance. And this is true when you get to these abstractions, CUDA, OpenCL, SYCL. There's no intrinsic reason, or ROCm, that any of them should give different performance. It comes down to the implementation. The big difference between them is the implementations, and then the openness to spanning different architectures, different vendors. So if you take a look, the kernel and all these things, Fortran, C, C++, my examples are the same. The magic comes in when you get the opportunity to direct where you want that work executed. So in many models, the way that you redirect your work, like in CUDA or ROCm, is that you compile a version of your program that predetermines that, hey, I want to run on an NVIDIA GPU, or I want to run on AMD, or I want to run on a CPU, and you build different binaries. The difference in thinking here with SYCL is I'm going to, at a program level, establish in my program what devices I'm hooking to, and I can be more flexible, and then I can direct particular work, and I can manage multiple devices. So if I happen to have an NVIDIA card, an Intel card, an AMD card plugged into a machine, my application can actually direct work to each and every one of them from a single binary. So the reason that this is important is we're undergoing a real explosion in computer architecture. Hennessy and Patterson, very famous computer architects that have written the most important textbook in the field, the quantitative approach to computer architecture. They've been talking a lot about this new golden age of computer architecture. I highly recommend reading it. I've got a QR code for their paper. It's just talks about a fundamental change in approaches of computer architecture that is affecting our lives going forward. So we see specialty devices for all sorts of computational workloads, and making an application able to take advantage of these is really the motivation behind SYCL and oneAPI, giving us the flexibility to use whatever type of hardware comes our way in the future. So, a SYCL program is really easy. I won't spend time dwelling on it, but there's a little bit of code that you say, hey, I want this run on the accelerator. Otherwise, it mainly looks like a program that's setting up computational workloads, and then dealing with the little things about directing what data and what work you want shared with an accelerator. So that's it. The vision here is really all about giving the same performance that you would associate with other solutions, but doing it in a fashion that is open to multiple vendors, multiple architectures, and very open. And it's very foundational, so it affects all the layers of software, frameworks, and such that may be built upon it. And I invite you to take a look at sycl.tech to learn more. And also, I've got a QR code for the Hennessy and Patterson paper here, which, if you've not read, I highly recommend it. It really sets up, the change that's happening in the industry. And with that, Joe will take us and talk about xPUs.
Hey, thank you, James. So what we're going to talk about is DPU programming and frameworks, also known as xPUs, SmartNICs, IPUs, NAPUs, function accelerator cards. There's a whole zoology, to reference the Cambrian explosion of terminology used here. Fundamentally, all of these devices follow a similar pattern in their architecture. And they're essentially microservers optimized for data flow and packet processing to provide accelerator, offload engine, and local services. When you look at how to deal with these kind of devices, ideally what you'd like to do is swap out software and program at a number of different levels, which is represented on the right. And in the industry, we're driving towards a set of common projects, for lack of a better word, to define the interfaces, define the layering, to make multi-vendor DPU deployments much easier to use and make DPU integration into your solutions, systems, applications, and architectures much simpler. There's some work on the hardware side, but I'm going to talk about a few frameworks on the software side that are current. So the first one is called Open Programmable Infrastructure. It's a project in the Linux Foundation. The founding companies are decorated around the edge of this slide. And what we want to do is foster an open ecosystem for DPU and IPU-like technologies. Again, zoology of terminology, it applies to all of the class of devices from the previous slide. So we have weekly meetings of various kinds for working groups. We have GitHub for open source contributions and API definition. There's a website that's becoming more informative and more useful. And our goal, again, community-driven, standards-based open ecosystem. That means we're going to have to define open source projects, specifications and standards, reference platforms, reference implementation for the API definitions, test suites and test cases, and then some proof of concept prototypes. So we want everything to be reusable and operate at all those interfaces that I outlined on the right. This is a public project. You can actually join and contribute at no cost. Everything is out in the open on this project, except the board budget stuff, but everything else is completely out in the open. So we'd encourage you to come learn and participate. Okay. As a sub-project of OPI, we have IPDK, which stands for Infrastructure Programmer Developer Kit. And it's an implementation of OPI across CPUs, DPUs, IPUs, and switches, or network processing units. Again, it has open source abstraction layer. It is using and will continue to use and leverage the OPI APIs, and it provides sort of a relatively complete package, especially where you care about P4 programs and their use, right? So if you want a custom P4 program, IPDK is a great way to go. And as I said, this is a formal sub-project of OPI itself. The next one that's in parallel to OPI is called DASH, which stands for Disaggregated API for Sonic Hosts. And again, it targets multiple applications and platforms. So it could be a smart NIC, DPU, IPU on a host. It could be a smart switch. It's really going after network disaggregation and high performance network appliances, and wants to develop a set of APIs for essentially cloud gateways, tunnel termination, and those sorts of things. And again, this is a fairly open project as well. It has a GitHub hosted under the Azure family, and it's fairly closely associated with Sonic. So, again, if you're interested in this aspect of data processing unit application, then Dash is a great place, and there will be cross collaboration across the industry on these things. That has already begun. OPI is only about 2 months old. Dash is, I think, 8 months old or 10 months old, although don't quote me on the exact time. So it'll take a little time for all these to really come together. Finally, if we look at APIs and frameworks on individual DPUs themselves, what is prominent right now is NVIDIA's DOCA. And again, it's layered in such a way that it presents the DPU functions to infrastructure applications in a way that the DPU can be leveraged. And NVIDIA is part of OPI, and many ideas and concepts are being contributed, and we expect that to continue. So if you're, this is just a good example of what can be provided by a DPU in terms of sort of a full-featured API. And again, making everything more open, building a common ecosystem is definitely a goal for all the players in the industry. With that, I know that was a fairly quick, broad brush, but I think each of these topics could stand a multi-hour session and lecture on. So, again, if you guys are interested, express your feedback, and we can come back and talk in detail about any of them. So now I'll turn over to Ben Walker from Intel to talk about SPDK and DPDK in some detail. Ben?
All right, thank you. I'm going to cover some lower layer stuff, the next level down from what we just covered. So I'll jump to the first slide here. We just talked about a bunch of XPU-centric frameworks that are, nice wrappers around, or they add a lot of value and control path and things like that, but wrappers around some lower level frameworks that implement things like device drivers and the actual data path in some cases, or integrate with hardware to make the control path actually set up offloads and things like that. What's really interesting in the way the industry has developed here is these XPUs are obviously very new devices, they're new concepts, but they're typically the most common case is they're built off of these existing software projects that have been around much longer than the concept of a XPU. Really, I'm talking about DPDK especially and SPDK. And these projects were not obviously created to work on XPUs. They were created to run on either switches or on servers, but they end up being fantastic software projects, fantastic fits for a environment like a XPU. So to go through this, I'm just going to really cover two use cases that kind of illustrate, one for DPDK, one for SPDK. So one common use case that people have when running mini virtual machines or containers in a cloud-like environment is they need a virtual switch. And so they have a bunch of VMs on a single system. These talk to each other over some virtual private network. They need a software switch that is routing between them. Historically, that would be implemented using a project like DPDK and Open vSwitch. In software, running on the server itself. And one of the great use cases of an XPU is let's offload the switch onto the XPU and hopefully get some benefits of hardware. So to do this, talk a little bit about what DPDK did. DPDK is a long-standing framework for doing this sort of packet processing. It's perfect for implementing vSwitches. It's used to implement real switches as well. It's open source. It's got a permissive license. And it runs on a wide variety of platforms, which actually turns out to be very important for XPUs, which are all implemented differently. And it can serve here as the core data path framework for software-defined networking. And it largely already is the sort of standard way to do this across the industry. So we can take that code that already exists and is production ready, and just as a starting point, run it on the xPU, just as is. And so the xPU may present multiple PCIe virtual functions to the host system, which then direct assigns them to VMs and containers. And these virtual functions would be NICs, Ethernet devices. And those would forward via some hardware path down into the SoC on the xPU that is presumably, running Linux maybe, or something like that, with DPDK on top. And it can just run the code it was running up on the host previously down on the xPU. That's kind of the starting point. And then, of course, we can add hardware accelerators to the xPU to do this better or faster or more efficiently. And we can use DPDK or projects like that to scan the system to see, hey, are there offloads available? Can I set up a full hardware path for this particular case? And then go do that, implement some control plane work. And, if it can offload to hardware, it does. And if it doesn't, it falls back to the existing software path that we know works and is battle hardened, that was in DPDK and projects like OpenVSwitch. So it ends up being this sort of hybrid solution, I think, in the long term. But the easiest way is just move the software to the xPU at the beginning. Okay, so
Hi, I think that we've just lost audio there. My apologies for that. Ben, are you able to hear us? Ben's here, but it appears we've lost the audio. My apologies for that. I can hear somebody typing furiously. Who's that?
I apologize. I was just told I lost audio, and
Yeah. Hi, Ben. Welcome back.
Okay, I rebooted my headset. I don't know what happened.
Excellent.
I'm here.
Well done, you. Okay, just carry on with your presentation. Thank you.
Okay, I'm going to just jump right into the storage one. So I'm going to do a storage use case now to talk about SPDK and its use. So we have a very similar case to the networking side, where we need to present a bunch of virtualized block devices into VMs or containers. And it's much the same concept, except now we're sharing typically physical disks or networked devices into these VMs, and we may be partitioning them or doing some sort of storage service on them. And the ideal case is really that we want to present either NVMe devices into these VMs, what look like NVMe devices, that's ideal, or VirtIO block or SCSI. And this is mostly because this is what the guest operating systems and the VM BIOS have drivers for. So we can do that with software, and that's how it's often done today. There's a software virtualization process that is emulating NVMe devices or VirtIO devices into the VMs. There's all sorts of work in SPDK and in other projects to do this, and we can offload that work to an xPU, just like we did on the networking side. So the most common framework for doing this, open source framework for doing this, is SPDK, where I'm a core maintainer, so I'm very biased. It is a long-standing framework, again, much older than the concept of an XPU, for doing these sorts of things. And it is much like DPDK, but for storage. So it's open source, it's BSD licensed, it runs on all the same variety of platforms. And it serves as the core data path framework for a lot of the industry in this area. Okay, so again, the concept is we have an XPU and it may have a piece of hardware that can present NVMe devices using SRIOV, or can present VirtIO block devices using multiple physical functions or SRIOV even. That piece of hardware could be a dedicated chip, or could be an FPGA, something like that. There's lots of different ways to implement this, but you have some piece of hardware that presents a set of PCIe devices to the host. Those will appear to be NVMe devices or appear to be VirtIO block devices and get passed through to the VMs for their use. And then commands sent to those devices get forwarded down into the XPU. The XPU is running SPDK, where it is emulating everything about the device, including like the register reads and writes. So it's pretending to be an NVMe device, but it's just a software implementation typically. And SPDK is able to forward those I/O to either local devices or out over the network over various network protocols. There's lots of different network protocols supported in SPDK. And SPDK also provides a framework for plugging in custom logic into that block stack in a way where you can run it up on your host system, test it out, it'll all work, or you can run it down on the XPU, and it's the same software. But just like the networking case, the most common uses here actually add on top of this software layer, the software data path, hardware accelerators. And so, SPDK is becoming very aware of hardware accelerators that are available to do various things, crypto compression, full data path offloads, are coming. So in some cases, SPDK, acts as just a control plane to set up the I/O path, and maybe it's handling the admin path or the control plane in software only. So with that, we have gone through kind of the next layer down from the high-level XPU frameworks down into the data path frameworks, and I'll pass it over to David, who's going to talk about computational storage.
Great, thank you. So computational storage, I will give an overview and review the benefits and get right into the programming of a computational storage device. So here's the problem statement that data processing resources are truly misbalanced. The picture on the left shows basically a large storage pool where our data would be stored. And then the compute is far downstream, and in between is this little network conduit where we see bottlenecking. And so that's not the best situation for application developers and customers. And as you can see in the drawing on the right, that actually limits the performance with that network constriction. However, the resolution to that is computational storage is one proposed solution. And so here, by bringing the compute to the data, one fancy term is called in situ computing. We're basically enabling a scalable situation where we can add compute resources to scalable data resources, and that in turn will scale performance, because we're not so dependent on that network conduit anymore. The benefits of computational storage are host offload for solutions in data analytics and rudimentary data function management like compression, encryption, filtering, these sorts of things. If we're able to offload the host processor complex from these tasks, or increase performance by offloading specific functions in data analytics, that's really good for applications. It also reduces the data movement because we're working on the compute on the data locally. And that's really good for green computing as well, because less power to move that data. It's application performance focused, and also there's some security benefits in taking this approach too, because not everybody wants to put their data up in the cloud. So here's what it looks like from a block diagram standpoint. So the left side is our classic well-known architecture where we have an SSD block, we have a CPU block and supporting DRAM, and we will get that networking bottleneck. This is at the, I suppose, the micro layer where we're just simply connecting an SSD to a CPU. And if that CPU is overloaded, we're going to create a bottleneck. You can actually expand that and illustrate with, say, a moving data up to the cloud, where going through a series of networks, they could also be bottlenecked and introduce further latency, which constrains the application performance. On the right is the computational storage architecture, where here you can see in that SSD block, we actually have instanced a compute engine where we're able to offload processes and run them where the data resides. And that provides us with that scalable performance boost and also green computing boost, because we're doing it all at the local level. So now that we understand a little bit about computational storage and the benefits that it provides, let's get into the programming methodology. So what we've really rigorously spent time this last year is to develop an industry standard approach to programming computational storage devices and arrays. And so this has been done with our home organization in SNIA, where a computational storage API has recently been released an 0.8 version to complement the computational storage architecture spec, which is at 1.0. I would highly encourage you to take a look at those specifications for further information. So that API spec defines the methodology for host applications to initiate commands to computational storage resources, for example, scan queries, which I'll show an example shortly. In parallel, we also have the NVMe TP4091 spec, which I look at as the programming tunnel down into the drive. So let's say you had an FPGA as your local compute engine within the within the computational storage drive. You're actually able to issue commands through that TP4091 tunnel and enable that accelerator to support specific functions and basically turn on and be that additional resource to the application. So you can send down a command and then send it back the result in a high level abstraction that an application developer or end user can understand. So that TP4091 is part of the NVMe 2.0 spec. And so I would also encourage you to take a look at that. And then here, so this is one example out of many. Computational storage is actually ramping in significant interest across our community here and beyond, given that value proposition I mentioned earlier. In this case, this is one example where we could take a database application and instead of burdening the host processor to run all the scan queries to search through a database, in this example Postgres, we can, in that blue block, have a custom scan block which will enable specific functions to go through that blue stack on the right and drop down into a compute engine within a computational storage device. So just the sequence here would be build the open source software module, and with that custom scan extension that I just mentioned, and that can be done using the computational storage API from SNIA. The next would be to enable Postgres to deploy that custom scan extension by just simply modifying one single line of Postgres code, and there's no Postgres recompilation required. So this is, we've spent a lot of cycles making sure that it is almost transparent to the application user to have this additional feature available to them. We load the NVMe device driver into which enables 4091, and then we run the application on the drive itself, and we report the result back. And the result typically will, because we're running it locally and we've offloaded the host processor, we're able to see 2-3x performance boost on the scan query and then also, because we're not moving the data, we've totally freed up the host to do other fun things. And because we haven't moved the data up to the host, we're actually doing our part in green computing to save the earth. So computational storage is definitely not just on the horizon, but is beginning to get enabled across our customer base today. So with that, I will hand it back to our wonderful moderator, Alex, to close us out.
Thank you, David. In fact, we've got enough time to ask a few questions. So I'm going to do that. But first of all, we've covered quite a lot today. There's been a huge number of acronyms. I'm all acronymed out. But I'd like to ask the audience to, first of all, if they have any questions, to please make them. And secondly, to make commentary on what they would like to see us cover in a little bit more depth. Use the feedback text there as you leave the presentation today. And don't forget to score us as well. But while we're able to, I'd like to ask a few questions. And I think my first question would be to, I think, David, because, or certainly perhaps John as well, about computational storage. Are there any vendors selling any computational storage stuff at the moment, or is it coming down the pipe in a few years' time?
Sure. So yeah, there are a number of vendors that are already selling complete solutions. ScaleFlux is one. Samsung is another. So we've actually been in this business now for 2 years, and we're building our second generation smart SSD for prototyping now, and it'll be in full production next spring. And I will say just candidly that our end customers, which are the system integrators, and their end customers, which are the application developers, are finally coming around and seeing the value that computational storage products and solutions offer to them. They're realizing the benefits today, from data analytics to data management to security types of applications.
So a limited number today, but very definitely coming to an outlet near you soon.
Yeah, I would say it's ramping aggressively now, which is great.
Okay. And the next question is for John Kim, although I'd like John to start the conversation because I think we might get interesting answers from others on the presentation today as well. There's that old cartoon by XKCD about, having 13 standards, and there was one standard developed to rule them all, and now we've got 14 standards. Are we in danger of having an awful lot of framework standards and thinking that we can have a single, or at least reduce the number of framework standards? I mean, what is going to take place in terms of standardizing frameworks in that sense? And by the way, will they be open source or will they be commercially available ones?
So I believe that will end up with mostly open source, and where the various open source projects and standard defining organizations cross-reference each other. That's what we're driving for, at least from a OPI perspective, as well as a SNIA perspective. We want to reuse existing APIs and collaborate across the industry to have a spanning set of APIs to cover all of the solutions and use cases. That takes some work, but in our OPI charter, for example, we explicitly say we want to reuse APIs where they exist and not redefine them. Then if you have to tweak them or adapt them, then that goes in OPI. We're not going to try to compete or unify as in one grand standard to rule them all. That didn't work for Sauron in Lord of the Rings. It didn't work in the XKCD cartoon. It never works. However, you can cross-reference and have a spanning set to cover all of the sub areas, we believe.
Yeah, John Kim, what's your opinion on that?
Alex, I apologize. I missed. I got a call. I missed the question. Was the question about whether we should have just one API or multiple APIs?
Yeah, which is going to win? And is it commercial versus open source, or is there going to be a set of APIs that coalesce together? And where do you see this going in terms of frameworks?
Yeah, I believe there will be some coalescence around a set of open source APIs, but I don't think they're going to, that everything will move there. I believe at least for a long time, there will continue to be people using some of the vendor specific or proprietary frameworks for some things. And then they will use the open source or open source multi-vendor framework for others.
Okay, thank you. James, I've got a slightly different question for you. In my experience, when I was an application programmer, parallelizing stuff was really hard. And I don't mean programming languages and the facilities that we had didn't allow us to parallelize. It was that your brain found it really difficult to find things to parallelize. How do these frameworks help us parallelize? I mean, in particular case, in point of SYCL, I mean, that is a great tool set, but what does the programmer have to think differently about to be able to take advantage of that?
That's a great question. Finding parallelism is the key job of a parallel programmer. And the best we can do with tools is give different ways to express that. So C++ with SYCL adopts a kernel style method of expressing a problem. And basically the idea there is you think of an operation that you need to do many times on different data, like, if you want to brighten an image, you want to add, 25 to every pixel. And you express that as a kernel and say, apply it to the entire image or set of images. That's a very simplistic way to think of it. That's what kernel programming fundamentally is about. And kernel style programming is something you see with CUDA, with OpenCL, with SYCL, with the HIP approaches and ROCm. That's one way. But I think the real answer here is we have to keep exploring more and more domain-specific ways to allow people to express their parallelism. Getting down to C++ and doing a kernel, or doing loops with OpenMP and Fortran and C, those are both very valid ways to do parallelism, but they don't necessarily click for every application. So I think we'll continue to see people who design frameworks, who design libraries. One of their big challenges is offering interfaces that sort of guide the programmer to get the benefits of parallelism without having to work out all the low-level details. Sorry if that seems like kind of a high-level answer, but I completely agree. Parallelism's not become easy. The way we make it easier is offering more ways that the programmer expresses it.
Yeah, I was thinking of, for instance, in asynchronous programming, it became a little easier when Node.js came along, but it didn't help programmers think about what it was they were attempting to make asynchronous.
Yes.
There's a bit of impedance mismatch between the brain and some of the tools that we have at the moment, I suspect. But I understand your answer fully. That's good, thank you. And Ben, I've got a different question for you. Hopefully your headset will stand up and not give us issues. But my question for you about SPDK and SPDK in particular is, what direction is it going in? Is it going up the stack or down the stack? I'm having difficulty working out which direction it's heading.
I mean, both to some extent, but I would say primarily right now, it is moving down. It is certainly heavily focused on the xPU use cases, which is running in an embedded environment. So it's getting a lot of focus on memory use and efficiency and portability. It's also likely going to be heavily involved in enabling computational storage via NVMe 4091 enabling. So it's used in a lot of higher level stacks, but SPDK itself seems to me the last year or two to be moving downward, closer to the hardware, even closer than it already was before. I mean, it already contained device drivers and was pretty low level. Mm-hmm. But I think it's going to continue to play in that really low level space. And then the higher level frameworks on top of it will expose it to various kinds of high-level software.
Okay, thank you. And Joe, I've got one last question for you. Can you describe and I know you're very involved in the standardization process. Can you describe very briefly the organizations, the standards organizations that are taking part in this? Just a quick 5-line summary. Who's who in the standardization process?
Right. So Linux Foundation with Open Programmable Infrastructure and its subproject IPDK.
Mm-hmm.
We have SNIA because there's an abutment to computational storage technical working group, and then there's a new xPU task force. We have Dash, which is focused on tunnel and cloud gateway APIs. And then we have the whole army of existing SDOs. For example, NVMe.org with the FMDS. We have Redfish with DMTF. We have other organizations of that type that impinge. There are multiple open source projects. You can see several of them referenced from OPI, say. So, for example, OTEL and SecureZTP have been agreed upon for those parts of what the DPU should do within OPI. The P4 programming itself is a standard we rely on. And there's more, but that's kind of the top of mind one for DPUs.
Thanks, Joe. I mean, I think I put you on the spot there, but that was I think it demonstrates the life in this, that there's an awful lot of interest. There's a huge amount of experimentation going on, and we're in the early days yet, and a lot of this will settle down and get some sense and shape around it as we proceed through, evaluation and experimentation, and actually move on to commercially available products that are using these technologies and these frameworks. Gentlemen, I'd like to thank all 5 of you for presenting today, and to thank our audience for coming along. And as the audience leaves, I'd really like them to give us some suggestions, an indication of what they would like us to cover next, and what you would think of these kind of presentations. Rate us on a scale of 1 to 5. 1 is, I wish I'd gone and played golf. 5 is, more please. And I'd like you to talk about this. And we'd be immensely grateful for your feedback. It's very important to us. In the meanwhile, I'd like to thank John, James, Joe, Ben, and David. And goodbye from me as well, Alex McDonald. Take care and have a good rest of your day. Bye now.